Good day. Our topic for today is about limits of exponential functions. Now, let's have a short talk about exponential function. Exponential function is very useful when it comes to analyzing the number of cases of coronavirus since 2020. And when we say flatten the curve, we want to make the number of cases to be constant or to be flattened. And when we say flattened, this curve will be in this form. We want to make sure that it is flattened like this. All right. So which means that the number of cases or infected human beings stop already from a certain value. Let's say this value. Or if we're talking about the additional number of cases, we want to make sure that this curve will be like this. All right. So, which means that there are no more additional infected human beings of coronavirus. Okay, and I hope this will be, or the curve will be flattened already by 2021, okay, with the use of exponential function. But for now, we're going to deal with the limits of exponential function, all right? Now, let's go to the first theorem of exponential function. It says here, the limit of a raised to x minus 1 all over x as x approaches 0 is equal to the logarithm of a base e. All right, so a here is the base of the exponent here in the given. So this is the formula that we will be using in solving the limit of exponential function. And if ever, whenever the base here is e, then this becomes the limit of e raised to x minus 1 all over x as x approaches 0 is equal to the logarithm of e base e is equal to 1. So therefore, when we talk about if the base is equal to e, which is the Euler's number, right, 2.17, something like that, and then the value of this expression of limit is equal to 1, okay? So you can use the natural logarithm also in evaluating the limits of exponential function. So let's apply this theorem. Let's talk about problem number 1, which is the limit of a raised to 3x minus 1 all over x as x approaches 0. Now the question there is, how are we going to use or apply the theorem that we discussed here? Okay, again, the limit of a raised to x minus 1 over x or all over x is equal to the logarithm of a base e. Now, I just want to emphasize this, that this x could be a function, right? Whatever function that we have, it could be a trig function or a 3x or a polynomial or whatever. However, as long as the exponent that we have here is also the same as the base, then we can, or the denominator, then we can use this formula. Okay, so in number 1, now how do we solve this? So let's just change the color. So that's the limit of a raised to 3x minus 1 over or all over x as x approaches 0. Now, the theorem 1 could be applied here whenever the denominator is equal to 3x. So we can add 3x, or we can multiply the denominator by 3, which becomes 3x. And of course, we need to multiply the numerator by 3 as well in order to make sure that there will be no changes in the given function. All right, so it's just like you multiply the numerator by 3 and also the denominator by 3, so which implies that it's you multiplied the given expression by 1. All right, so here we can now apply the limit since the exponent is now equal to the denominator. Okay, so we have the limit of a raised to 3x minus 1 over or all over 3x as x approaches 0. Okay, we can take the limit times the limit of 3 as x approaches 0. So here, let's solve. Right, and based on the theorem number 1, what is the limit of a raised to 3x minus 1 all over 3x as x approaches 0? This is equal to the logarithm of a, which is the base, base e, which is the Euler's number, times what is the logarithm of this? The logarithm of 3 as x approaches 0 is always 3, which is equal to 3 times the logarithm of a to the base a. All right? So this is now our final answer for problem number 1. And I hope we get the same answer. Okay, so in problem number 2, I want you to answer this by yourself and uh, try to pause the video first before playing the video, all right, before checking the final answer. And let's see if we'll get the same answer. All right, so in count of 3, kindly pause. 3, 2, 1, 0. Okay, and let's solve this and let's check if you have the same answer as mine. All right. So the problem number 2 says that find the limit of e raised to sine x minus 1 all over x as x approaches 0. Now here, the base is e and the exponent is sine x. So for us to use the theorem of exponential function, then we need to make sure that the denominator is the same as the exponent of the given expression, okay? E raised to sine x. So if we want to uh, express this expression where the denominator is equal to sine x, all right? So let's solve that. Okay, so we have the limit of sine x. So let me change that. Okay, so let's do it again. So the limit of e raised to sine x minus 1 all over, okay, x times, all right, again, we want to place sine x on the denominator, all right, for us to apply the given theorem. So what we do is we multiply both sides by sine x. Both sides means the numerator and denominator and sine x. So multiplying the numerator and denominator by sine x is just like multiplying it by 1 as x approaches 0, of course. Okay, so let's re-express let's try expressing the given in terms of the similar as the one given in the theorem. So that's limit of e raised to sine x minus 1 all over sine x, okay, as x approaches infinity, times, all right, so the denominator sine x was placed on the denominator here together with the e raised to sine x minus 1. And we have here sine x. And of course, the x here will be written below the sine x. So let's use the red one. I mean the white one. Here we go. Okay. So again, this expression is just equal to this expression. We just commute some of the factors in the given expression. Okay. So as we could apply the theorem for of the exponential function. So let's simplify this. Now let's take the limit of each factor. So we can have the limit of e raised to sine x minus 1, or sorry, minus 1. Minus 1 is a base. Okay, minus 1 all over sine x, same as the exponent, as x approaches 0, times the limit of sine x over x as x approaches 0. Okay, so now let's take the limits of the factors. Now, what is the limit of e raised to sine x minus 1 all over sine x? And the expression is similar to the theorem, right? So it means that all the conditions were met, so we can apply the theorem now. So the answer here is, okay, the answer here is equal to the logarithm of the base, which is equal to e, base e, okay, times, what is the limit of sine x over x? The limit of sine x over x as x approaches 0 is equal to 1, okay? So this becomes the logarithm of e base e, and based on the property of the logarithm, if the base and the number here, all right, are equal, then the logarithm is equal to 1, okay? So the answer here in number 2 is equal to 1. All right, so we have 1 as the final answer. And I hope we get the same answer. And let's work on number 3. And again, try to answer this on your own and pause the video before you see the final answer. Okay, so how do we solve the limit number 3? Limit of 5 raised to 2 plus x minus 25 all over x as x approaches 0. So in this case, we want to make sure that we can express this in terms of a given theorem. So let's remember the theorem. The theorem says that the limit of a raised to x minus 1 over x as x approaches 0 is equal to logarithm of a base e, right? So you want to express the given in terms of this. But the question is how? Okay, so let's try analyzing the given expression. So the limit, look at this, 20, this is 25. We want to make this one such that it will be the same as the given in the theorem. And for us to make this one, we can factor it out. Okay, 25 can be factored out if the first term of the numerator can be expressed as 25 times a certain number. Okay, and 5 raised to 2 plus x is equal to 5 raised to 2 times 5 raised to x minus 25 over x as x approaches 0, right? So here, we can now see that we can factor out 25 here. So that's the limit of 25 times 5x minus 1 all over x as x approaches 0. So since 25 is constant, then by the limit property, we can place this constant or coefficient as a coefficient of the limit. So that's 25 times the limit of 5 raised to x minus 1 all over x as x approaches 0. All right, so let's take the limit of this. Now, since the expression is already similar to the one that we have here, then we can now apply the limit, all right? Why? Because the exponent x is same as the denominator x. So here, the limit of this is equal to the logarithm of the base, which is 5, and of course, base e. Okay. All right, so the answer now is this, 25 times the logarithm, or 25 the logarithm of 5 base e, or you can also say it's 25 log 5, all right, over log e. Or you can also express your answer in terms of natural logarithm ln 5. You can also do that, okay? And these three expressions are just, or they have equal values, okay? So our answer is this, and we got the correct answer, all right? And I hope you get the correct answer as well. Okay, in number 4, the limit of 5 raised to x minus 1 all over 2 raised to x minus 1 as x approaches 0. And then again, we want to express the given problem in terms of the expression given in the theorem. So how do we do that? Okay, now look at the numerator. The numerator is already good to go, but we lack x on the denominator, okay? And also the denominator here, 2 raised to x minus 1, is just like the expression on the numerator of the theorem, but it lacks x on the denominator. Okay, so that's our goal for now. We want to place an x in the denominator of 5x minus 1, or 5 raised to x minus 1, and also the denominator of 2 raised to x minus 1. So let's try to express the given problem in terms of the theorem. So we could have 5 raised to x minus 1. Okay, we can place x here, right? And since we place x there, we should multiply the numerator by x as well, such that it's same way as multiplying it by 1, correct? And we have a denominator of 1 over a denominator of 2 raised to x minus 1. Okay, and again, we want to express this the same manner as the one in the theorem. So how do we do that? We can express this, okay, the 2 raised to x minus 1 over x, right? But how do we do this? For us to do that, we need to multiply this by 1 over x, right? Okay, and also this one by 1 over x, if that is so, okay? All right, so let's do it now. As x approaches 0, or there is another way to do that. Let's do that later, okay? So we have the limit of 5 raised to x minus 1 over x as x approaches 0 times, all right, we can do that. What can we do about this? So we can write the 1 over 2 raised to x minus 1 over x because of this. And we have x, and we have 1 over x. There we go. So let's simplify this. I can simplify this. I can cancel this out, right? And I can take the limit of this. So the limit of 5x raised to x minus 1 all over x as x approaches 0. Okay, times the limit of, we have 1 over 2 raised to x minus 1 all over x as x approaches 0. Okay, here we go. So what is the limit here? And the limit here is equal to the logarithm of the base of the given, that's 5, and here base e, okay? And here, the limit of 1 is 1 over, what is the limit of this expression? This is equal to the logarithm of the base 2 e, right? So this becomes the logarithm of 5 base e over the logarithm of 2 base e. So you can express this in this manner. However, we can still simplify this using the property of logarithm, which is change of base, right? The reverse of change of base. So we can combine this by placing 5 here and 2 as the base. All right, so we have logarithm of 5 over 2 is equal to the limit of the given problem. Okay, so I hope we got the same answer. And by the way, as I said, there's another way to do this aside from the one that we did, this one, all right? I think this one is quite complicated. Let's try to make another way. So we have, again, we want to express this in terms of the given theorem. So that's the limit of 5x raised to x minus 1 all over x. Okay, since we divide this by x, we need to multiply it, the numerator, by x as well, such that it's same way as we're, what's this? We're multiplying it by 1. So 2 raised to x minus 1 as x approaches 0, something like that. Okay, and here, so we can take the limit of each factor. So we have the limit of 5 raised to x minus 1 all over x as x approaches 0 times the limit of, Now look at this, guys. The 2 raised to x minus 1 is on the denominator, and the x is on the numerator. But in the given theorem, okay, it stated that this one is in the numerator and this one is in the denominator. So we can do something about it, okay? We can take the reverse or the reciprocal of the given expression. So we have 2 raised to x minus 1 over x. Since we took the reciprocal, therefore, we raise it to -1 as x approaches 0, right? Okay, so we have, let's take the limit for each factor. So this one is equal to the logarithm of 5 base e times, what's the given expression, in the given expression, 2 raised to x minus 1 all over x raised to -1, the limit can be, or we can take the limit of the inner term or inner expression. Okay, so let's take the limit. The limit of 2 raised to x minus 1 all over x as x approaches 0 is equal to the logarithm of 2 base e raised to -1, right? And let's simplify. So this becomes the logarithm of 5 base e over, this is 1 over, right? So 1 over is just equal to logarithm of 2 base e, which can be simplified into the logarithm of 5 base 2. Or we can also express this in terms of ln 5, or the natural logarithm of 5, and the natural logarithm of 2, right? So let's check if we have the same answer as before. Here we go, log 5 base 2, log 5 base 2. Okay, so we got the same answer. Okay, so I hope we got the same answer. And let's work on number 5. Again, try to answer the given before showing or looking at the final answer. So let's simplify. We have this. And as we can see, we have already x on the denominator, but there's no -1 or -1. So let's see what we can do with this, okay? I can express this in terms of, okay, let's do that here again. The limit of e or a raised to x minus 1 all over x as x approaches 0. All right, so I want to express this given in terms of this, but what I can do now is I can, okay, divide the terms into two. I mean, the expression into two terms. So e raised to 9x over x minus e raised to 5x over x as x approaches 0. But in this case, we don't have -1, right? We have only the first term. So what can we do now? So we need to find a way such that we can, okay, we can express it on similar to the given theorem. So let's find a way. Okay, let's find a way. All right, so for us to do this, let's see what we can do. We're going to copy the limit as x approaches 0. Okay, e raised to 9x over x. I could subtract this by 1 over x, such that I would get e raised to 9x minus 1 all over x, right? Also, since I added -1 over x, I need to add 1 over x as well, such that it's just the same as adding it by 0. And copy e raised to 5x over x. Here we go. Okay, now I can now associate some of the terms here. Okay, so let's do that here. The limit, okay, as x approaches 0, and I can associate this. Okay, let's do the association here and here, right? So let's do that. Let's do the red one first. Okay, I can say that e raised to 9x minus 1 over x minus e raised to 5x minus 1 over, or all over x, right? Oh, sorry. We should be using blue. Okay, we should be using blue here. Okay, so that is e raised to 5x minus 1 all over x. Here we go. All right, so now the question there is, how do we simplify? Now, to simplify this expression, we can now use the given theorem, right? By, okay, so we have, let's simplify, the limit of e raised to 9x minus 1 all over x as x approaches 0 minus the limit of e raised to 5x minus 1 over x as x approaches 0. Okay, and we can now multiply both numerator and denominator by 9 on the first term. So this becomes limit of e raised to 9x minus 1 over 9x times 9 as x approaches 0, y times 9, because it's just like we're multiplying it by 1, minus the limit of e raised to 5x minus 1 over x as x approaches 0. Since this is 5x, I can multiply this by 5x in the denominator and multiply the numerator by 5. All right? Such that it's just like multiplying it by 1. So this becomes, I can factor out 9. So the limit, oh, I think we don't have space anymore. Okay, here we go. We can write our next step on the next slide. Okay, but what I can do now is, all right, I can put this coefficient, this 9 as a coefficient, and this 5 as a coefficient. Okay, so let's do it on the other side. Okay, on the other slide. Here we go. So we have, okay, that's 9 limit of e raised to 9x minus 1 all over 9x as x approaches 0 minus 5 limit of e raised to 5x minus 1 all over 5x as x approaches 0. Okay, so we're now ready to simplify. And let's use white. Okay, so, okay, and we successfully expressed the given terms in terms of the given theorem, right? So this becomes 9. And what is the limit of this term? So that's the logarithm of the base e. The base e here is e, so it's e. And based on the theorem, the base of the logarithm should be e. Okay, minus 5. As well here, similarly, the answer here is logarithm of the given base, that's e, with a base e. Okay, and using the property of logarithm, now if the base and the number here, all right, so let me just change the color, are the same or equal, then we can cancel this out, and this becomes 1. Okay, so the answer here is 9 minus times 1 is 9, minus 5 times 1 is 5, and this is equal to 4. That's why the answer in number 5 is equal to 4. Okay, so let's go to number 6. Okay, and how about this? We have 3 raised to x minus 2 raised to x all over tangent x as x approaches 0. Now, same thing. We're going to apply the theorem for limits of exponential functions. So we have the limit of, okay, here we go. or we can rewrite this in this form. 3 raised to x minus 2 raised to x, right, times 1 over tangent x. Okay. And since as x approaches 0, of course, since our aim here is to multiply or to express this given first factor with a denominator of x, therefore we need to multiply the expression by x such that it's just like we multiplied it by 1, okay? Or we divide this by 1 and we multiply it by 1, since we can cancel the x. Okay, so let's simplify the expression. This becomes 3 raised to x, all right, over x, okay, minus 2 raised to x over x, and this is x over tangent x as x approaches 0. Okay, so the question now is, what are we going to do with this? So it's just like the same thing that we did in number 5, if I'm not mistaken. Let's go back to number 5, yeah. Now we're going to add terms such that this will be expressed in terms of the given theorem. So this becomes the limit as x approaches 0. This becomes 3 raised to x over x minus 1 over x plus 1 over x, such that it's just like we added 0 or we added nothing, minus 2 raised to x over x times x over tangent x. Okay, so now we can let's rewrite or simplify the expression such that we can see how to deal with the problem. So we have the limit of a given expression. So we have 3 raised to x minus 1 over x minus 2 raised to x minus 1 over x, right? Times x over tangent x. Okay, here we go. So in this case, we have now seen an expression similar to the given theorem here, the first term and the second term. And we have another expression here. So let's deal with this. Okay, this part. So let's go to the next slide. So let me just copy the limit, or let's take the limit of all the terms, all right? So I have the limit as x approaches 0 of the given expression. Okay, 3 raised to x minus 1 over x minus the limit of 2 raised to x minus 1 over x as x approaches 0, multiplied by the limit of x over tangent x as x approaches 0. Okay, here we go. So let's simplify. Let's simplify this. What's the answer here? The answer here is based on the theorem. That's the logarithm of the base here, okay, with the base e, minus the logarithm of the given base 2 with the base e. Okay, times, what's the limit of x over tangent x? Now, how do we deal with this? Okay, so here, let's try to simplify or decompose tangent into simpler trigonometric functions, such as the limit of tangent is equal to sine over cosine, right? So this becomes x cosine x over sine x as x approaches 0. Okay, and here, so our problem now is the second factor. So let's simplify the given expression here. So we have the log 3 over 2 using the property of logarithm. Since it's minus, then we divide the bases. I mean the numbers 3 and 2, the argument 3 and 2. So we have Oh, since I can see x over sine x, I know that there's a theorem that says the limit of x. Okay, the limit. Let's recall a given theorem about trigonometric. Okay, trigonometric. The limit of trigonometric function. So we have the limit of sine x over x as x approaches 0 is equal to 1. Or we could say also that the limit of x over sine x as x approaches 0 is equal to 1. So we can apply this, okay, theorem to solve for the limit of this given factor. So we have the limit of x over sine x as x approaches 0 times the limit of cosine x as x approaches 0 as well. Okay, so now we can now take the limit of these two factors. So let's solve it on the next slide. And I will copy the first factor. So that's, well, let's use white. The first factor is the logarithm of 3 over 2 base e times, okay, what's the limit of x over sine x as x approaches 0? That's equal to 1. So that's 1. And how about the limit of cosine x as x approaches 0? Here, since 0 is a domain of the given function cosine x, therefore, we are allowed to do direct substitution. So what is cosine 0? That's 1, right? So therefore, that's 1. And our final answer is the logarithm of 3 over 2 base e, or we could write it as the natural logarithm of 3 over 2. Okay, so these are the answers that we could, these are the answers, all right? Or we can accept either answers. Okay, so I hope we got the same answer, which is the logarithm of 3 halves base e. All right, and that's it. And good luck on your exam.